Have you ever wondered how Netflix recommends you shows, or how a simple algorithm is able to detect handwritten digits on a check? That's the magic of K nearest neighbors, or KNN algorithm. And today we'll uncover how this algorithm exactly works and how many use cases it has in different industries. It is one of the simplest algorithms in machine learning, yet it is so powerful. So let's dive right into it. So let's start with a simple example. Imagine you're in a huge library and you're on a quest to find books that are similar to your favorite novel, let's say the Enigma Code. How would you go about this? So you would look for something which helps you identify books that are similar to your taste given what you already like. So you might say, let's say if I want to find a book that's similar to the Enigma Code, I would probably look for more books by the same author. So that's one approach. Let's say more books from the same author. What else can I look for? I can look for similarity in genres. Similarity in genres. Maybe I can also look at the time when this book was published. What else can I look for? I can look for public reviews as well. But public reviews is not something that would help me identify a book by my choice. So this is a dicey feature. So let's label it as maybe, not necessarily. In this case, not necessarily. It can be a good indicator for whether a book is good or not in general, but not specifically if I have a choice. So I would look for things like this, and then I would try to find out where in the library these kinds of books are placed. And that's the exact idea of KNN. That in a nutshell describes the intuition behind KNN, which is K nearest neighbors. So what you do is you try to find out the similar points in your dataset to your given point and see what those similar points are behaving like, and then you conclude things about the given point in question. So if I have to formalize, and let's formalize the example, we chose publishing year and let's say average reader rating as well as the genres. And then my Enigma code is placed somewhere here. So if you look carefully, this is where my current book is placed. And then what I did was I took all the other books in my sample set and I gave them labels based on their genres. And then I also plotted what the average reader rating was in those publishing years. So I also plotted publishing year and average rating. So we took essentially three features. And now what we can do is we can say, okay, if I really want to restrict on my category of book, I would take only these ones which have the same category, and I'll see which ones are the nearest in that category to the Enigma code, right? So I would take that category, and then the nearest books, I would probably look into those if I find those books interesting or not. Good chance are they might be similar books, and then I might also enjoy reading them. One caveat that I want to point out in all of this is you should be very, very careful in feature selection. So what happens if I take public reviews without taking into account the genres? Maybe I'll get some book which is very, very similar in reviews or has exactly similar rating as the Enigma code, but that book might not actually be very similar to the book in question. That's a very important side note we should keep in mind, that the features that you are selecting should be reflective and should intuitively make sense that they are good features when you're trying to compare data sets in those features. Now, if I have similarity in genres and then I also take public reviews in account, then that becomes a very strong indicator, because now I'm first filtering out the same genres and then I'm taking what is the public opinion in that category. So be aware of all these caveats. And when we try to build a model, again, I want to emphasize on the practicality of it. We need to be very practical and aware on the features that we are selecting. Moving on. So I want to give one very interesting example before we move on to the applications and different industries in which KNN is used. And that example is of OCR system. So now what is OCR? OCR is basically optical character recognition. So essentially things that you write, is a machine able to read handwritten objects or not, right? And can it classify what letter or number it is? And right now you might think, okay, OCR is a pretty solved problem. Advanced neural nets can easily solve recognition problems, be it image recognition or character recognition. And you're right, neural nets are really good at solving this. But Think about it from the lens of 1960s and 70s. In that time, when the neural nets were not advanced and they were just in a very nascent stage, OCR algorithms were still working. And the first OCR algorithms that came up, the first set of these algorithms that came up were using KNN. Such a simple idea that we just explained, and that simple idea was powering things like OCR. So how was it doing it? So let's say I had these digits. How would I classify these digits? Well, you can say that, okay, what if I give you thousands of labeled data set of different handwritten threes, and then would you be able to classify it? The answer is yes and no, depending on how well did you do in terms of giving that data set and selecting your features, right? But let's say you did a good job in selecting the features that you want to use for your classification, and you gave a lot of labeled data set. Different people wrote all these characters in their own handwriting, so there will be variations of each, and you labeled all of this data set. So you had like thousands and thousands of variations of 3, 4, 5, 1, and so on. And then when you gave the new data set to the computer, it was able to predict based on KNN that this digit is 3, this digit is 4, and so on. Now I would urge you to think, what could be the feature set in this case? What are the things you would select on this labeled data set that you would use for further classification, right? And the hint to this is try to think of the image in terms of a pixel grid. That's a very good exercise. But if you want to dive with me, let's look at what features would you select for OCR. So let's take two features. First is R is equals to height by width. What do I mean by height and width? You take the first bright pixel at this point, and then you take the last bright pixel on this axis. You do the same on the horizontal axis, and then you have both height and width parameters. You take the ratio of that. Why are we doing this? Because it gives us a sense of how squished or how wide any given digit is, right? So that can be a feature. For example, in the case of 1, when you have a digit 1, your height is very high, but your width is going to be very less. Even if different people drew it differently, in the majority of cases, this height by width ratio is going to be somewhat similar for 1, which is going to be drastically different for something like 2 or for something like 0, right? So this is a way you have partially separated some part of the image. So this is 1. Another really good feature could be symmetry. And there's a very clever way in which you can define symmetry. So you can define symmetry like a summation of I intersection I bar divided by summation of I. Now what is this? What do I mean by all these summations, and what is I and I bar? So think of it in this case. Let's say you had this digit, and now if I were to draw a mirror image of this. So let's say I put a mirror here and I draw a mirror image of this. So I have something like this, right? So this is somewhat of an inversion. Just stick with me. I know my handwriting is not that good, but when I draw this image, now I will overlay this image on top of my original image. When I overlay this image on top of my original image, then how many of the pixels are lit? Remember that we already gave 0, 1, 0, 1, 0, 1 to each of this pixel in this grid. And now I have a mirror image which has a mirror image of those zeros and ones. And I am overlaying both of those pixels, and I'm only counting the pixels which have an intensity of 1. Put 1 only where there are both ones in that position. So in that grid, in the new intersected grid, you will put 1 as the value of the pixel if both those grids have 1 in them. Otherwise, you put 0. And you take the sum of all the ones in your total grid, divide it by the sum of all the ones in your original grid. What is the original grid? The original grid is the actual and original handwritten digit. Again, what are we trying to do? What's the intuition behind it? For digits which are symmetric, like 0 and 8, the mirror image is exactly going to be the same in a perfect world. Even if we assume people's different handwritings, the intensity, the intersection intensity is going to be high for symmetric images. And that's the key. Again, we have used or devised a mechanism to separate the digits a little bit more. And now you can keep thinking of more and more parameters that can be used. And this is an exercise because there are more parameters that people have devised and features which people have devised to separate these digits out. And using those features, if you use these features on this labeled dataset that we already have, you can apply KNN and see if now I see a new image which has a symmetry value of 0.5, which has a R value of 0.3, what can this image be? And then I look up what these two values are closest to in my dataset. And I'll say, okay, this is closest to images which have a label of, let's say 7. So my new image could be 7. And that's how you can do classification on this kind of OCR, right? So it's very, very interesting. Please go and try to explore more features that can be used, or try to think about more things, how you can separate the digits out. Think of how can you distinguish corner on edge cases. This is slightly more advanced in terms of feature building. So for KNN, the major thing you have to remember is you are trying to build features that can help you. So try to think of how you can classify different images or separate different images based on corner or edge. 0 does not have an edge. How would you build something mathematically that helps you discover whether or not your digit has an edge or a corner? That's a very good one. So explore that one, and let's move on. Let's move on to other areas where KNN can be useful. So we looked at OCR, which is a classification system where KNN is useful. So let me just mention it out. Classification system. And we have seen the example of classification. Now, there are two more primary pillars in which KNN is very useful. And one is recommendation systems and one is anomaly detection. And both of these places, KNN can be really leveraged to give us good results. So what could be some of the use cases in recommendation systems, let's say? So the one thing that we talked about was Netflix giving you recommendations on what to watch next. Let's say you have watched a lot of things on Netflix. Again, this goes back to the book problem, the Enigma code problem. Once you have some watch history, Netflix can predict based on that what you would like next. Exactly the same situation that we took in the first case, in which we were trying to find a novel in the library. Now Netflix is trying to find your next show based on the previous shows. But let's say you have just launched Netflix and it has no data on what you have watched or what you like. Still, it can give you some recommendations. So one thing is they can show you the trending things in your region. That's A. But what else can it recommend? It doesn't know what you like, but it does have data similar to people like you. It knows what people of your age, your gender, your income group or your region, right? It has these parameters. So it knows what people in these categories generally tend to like. So it can start with those recommendations, which are maybe not that perfect, but they are better than random luck, right? It can start with those recommendations, and as you build your watch history, it can fine tune those recommendations. Another one is anomaly detection. Why do I say this one is also a very important use case? So let's take another example. Let's say you have an account with a bank. Now this bank keeps your money safe. It allows you to deposit and take the money out as and when you need it. But what happens, let's say if you make a transaction in a new unknown location, very, very far away from your usual locations, and you try to take out very high amount of money. In that case, the bank has a fair reason to believe this can be a fraud transaction. How did it detect it? It detected based on the features like your usual transaction amounts, your locations where you usually transact, or how far away from your home or from those places you are, and a previous history of how many frauds were reported in that type of transactions or so on, right? We can think of more complex features as well. But primarily, if you are very far away from your usual locations and you are withdrawing a very different amount, the bank has a fair suspicion that this can be a fraudulent transaction and it can prevent it from happening. And that's what I mean by anomaly detection. You can use KNN to build very robust systems or methods that help us and prevent these kinds of things from happening. So that's a very useful case on how KNN can be deployed. Those are some of the systems in which KNN is generally used. Now, I want you to take a moment and appreciate what a simple algorithm this is and how vast the use cases for this are, right? And that's the beauty of this algorithm. Its simplicity, interpretability, and versatility is what has made KNN so powerful and so well used. And that's why we study KNN. And I hope this lecture made sense and you are able to appreciate the true beauty of KNN. If you enjoyed this video, do consider giving it a like and a subscribe. Thank you so much, and I'll see you in the next one.